Hi, I'm Brett Pemberton. I'm an engineer at Slack. And hopefully for some of you in the audience, Slack is where work happens. So we're an adaptive collaboration hub, and we provide channel-based communication, searchable knowledge store, and an integration layer where you can interact with lots of tools that you might need for your day-to-day job. I'm from the cloud engineering team. We're based out of Melbourne, and we support a lot of the internal teams at Slack and help them get their services up and running and give them the things that they might need, whether that's an AWS account, Kubernetes, whether they want Chef and Terraform, or whether they want to run in our edge regions. So Slack is similar to a lot of other startups out there in that we started doing something completely different and pivoted from it. In our case, we were developing a video game system called Glitch. We're also similar in that at one point we were just running out of a single AWS region. In our case, it was US East 1, and we had a lot of servers in there that were handcrafted artisanal pets that we loved and cared for, which is, I'm sure we all agree, not the best place to be. And at the heart of things, we're just a giant lamp stack. Popularity hit, and we had to grow to meet demand, so we tried a few different things to scale to do this. Firstly, we threw clouds at the problem, so we scaled horizontally and vertically. We swapped out some of the components of the lamp stack. We added in Vitesse for database clustering. We switched from PHP over to Hacklang from Facebook. We also added in application level caching in front of our real-time stack. This is a system called Flannel, and there's a write-up on it on our engineering blog if you're interested. It's a pretty good read. We also added functionality like calls to allow you to video chat with your colleagues, and some of these things that we did gave us the option to move the application out of US East 1 and closer to you. And we did this by spinning up edge regions. Initially, as an experiment, most of these edge regions were created by hand by an engineer in the AWS console. And again, it's a reality that some things start off like that, but it's not where you want to be in life. So once we'd proved that all of this worked and it was going to help our situation, from there we moved to Terraform to try and make our lives easier. Terraform made our life a lot easier for this. We were able to create modules for each of the different components that we're pushing out to the edge region. We could then use Jenkins, our old friend and nemesis, to make this reproducible and push these edge regions out live. We invested in auto-scaling groups to replace our handcrafted artisanal pets and replace them with scalable fleet. In reality, some of these servers were stateful, so scaling out is usually a lot easier than scaling in. But we had some incremental improvements, and it definitely made life a lot easier. So again, once we'd proved that this concept was going to work, Terraform was the way to go. From there, we went a little bit crazy and automated it a lot. We created Terraform modules inside of Terraform modules inside of Terraform modules. We figured we were going to be doing a lot of these edge regions, so we wanted to get it as automated as possible, and instead of taking a few days to bring up a new region, try and get it down to a few hours. And it all worked. We created a templating system called Stampy to do all of this work for us, and the edge regions were then being built by Jenkins, not by an engineer. To create a new edge region, all you would need to do was do a pull request containing a blob of JSON containing a few key bits of information about the region you were building. And from there, Jenkins takes over and builds it all out, scales it all up, and tests that it's working. So once we had this automation in place, of course, we built and rebuilt our regions constantly and spread them out throughout the world and tried to get in as many regions as possible, which all magically made everything great, except it didn't. So the reason it didn't, we need to go back to what's in a region. In our case, we had a lot of different things in this region. There's the call servers I mentioned earlier to help the video chat be low latency. There's image processing and edge file uploads owned by the web app team. There was the Flannel servers that I mentioned earlier, which terminate the WebSocket connections, owned by the Flannel team. There was the real-time services had servers in there. The monitoring team had monitoring servers in there to keep an eye on things and send alerts when things go down. They had Prometheus servers in there as well to gather metrics. and cloud engineering, we really initially only had a single server in there, which was a Bastion host to allow SSH connectivity. Recently, we've also pushed Kubernetes out to the edge, but even so, anytime we did anything to any of these regions, rebuilt it, disabled it, drained it, we were affecting about a half a dozen other teams besides ourselves. And that was creating some friction. We could see teams out there going, bomb, what the hell is this? Since when do we have servers out there? Or a team might go to update their servers in Singapore only to find they don't exist anymore. We deleted that stack yesterday. And on the process of updating, some of the teams had a little bit more automation and maturity than others. Some teams had embedded SREs who were helping them on the process, keeping their fleet fresh, healthy, putting in automated processes to handle all this. And some teams just weren't that big yet, didn't have that level of maturity, and they were basically iterating over the regions one by one, updating the servers by hand with handmade scripts. So for those teams that weren't as mature, us being in as many regions as we were was definitely causing them friction. So how can we help with that? Firstly, what we put in place was a way for service owners to decide what regions that they're live in. If the calls team don't want their servers to be up in Paris, no big deal. It's up to them. We're just providing the service. So we needed to make a way for them to be able to be in control of that. We also pared back the number of regions that we were live in. For the example of the west coast of the US, did we really need to be both in Oregon and in Northern California? Because in reality, using geo-routing for determining which region you end up in, you end up with sometimes 90% of traffic going to one region, and the other one's basically empty. So in that case, we had enough regions for redundancy reasons, so let's just scale that down and try and solidify where we are. So you can definitely go too far with your automation, and you need to keep an eye on your customers and remember that they're there as well. And for us, it was our internal customers that we needed to keep informed, and it paid off to keep them active in the decision-making process. So that brings me back to WebSockets. WebSockets, if you haven't used them, are a full duplex communication over TCP. They generally operate on the same port as HTTP and HTTPS, and Slack uses WebSockets for the client communication. They are great for real-time data transfer, and it's part of what makes Slack feel like a genuine conversation rather than posting on a web forum or something like that. But they can also make life interesting. So if you remember, we terminate the WebSocket connections at the edge, and that first time you connect to this to the edge and establish the WebSocket connection and establish the client connection, it's a really heavy operation. We need to talk to a whole bunch of downstream services to get a whole bunch of information to display in the client. What channels you're in, what DMs do you have open, do you have any unread messages in any of those, what team members do you have who are currently online, things like that. So it's a really time-consuming operation, and once it's established, everything works fine, but that initial process is definitely heavy. So what happens if that connection gets torn down for some reason and needs to be reestablished? Say the network has some interruption, say the Flannel server you're talking to gets shut down, your ISP sneezes, anything like that, you need to reestablish the connection, and that's a really heavy process. And what happens if it's not just you who's doing this? What happens if we sever the connections of an entire region worth of customers at once? That's a lot of WebSockets all trying to reestablish and all stressing downstream. And that can quite easily cause a cascading failure, disconnecting even more users, spreading worldwide, and bringing everything down. So it's a good thing we would never disconnect an entire region worth of customers all at once. Except we did that all the time, and it was a pretty bad scenario. So how did we iterate to improve on that situation? There were a lot of small and medium technological improvements that I'll get to later that we implemented to do this, but more importantly, there were some procedural changes we went through to identify where we can make these changes and how we can improve. First thing is a tabletop exercise, where you, as an engineer, sit down with pen and paper and basically write down how your systems behave. And in a scenario such as getting your client socket disconnected, what's going to happen at the client level? What happens next? What's it going to do? How's it going to behave? What about downstream services? How are they all going to interact? And once you've written down all that on paper, you can then move to disaster piece theatre, which is a controlled form of chaos engineering that we practice at Slack, where it's a pretty simple process. You get a room full of interested people, you all bring up charts and graphs, and then you all watch as you do the thing that you just identified. In our case, how does the client behave on a WebSocket termination? Easy. Let's just disconnect them, see what happens. Do it in dev at a small scale, see how that reacts, see if it's going to cause problems if you do it in production. If it's not, let's just do it in production, cut off the connections for a bunch of people and see how the telemetry matches up with the predictions you made on paper. A lot of times, comparing those results can be very interesting, and there's a lot of surprise learnings that you can come up with. And a lot of times, we will see things in dev that make us decide not to go ahead with production. Instead, you might come up with a few interim things you want to put in place before you do this live, come back in a couple of weeks, and then do it again, see how it reacts. And looking at failures in the wild. After a postmortem, any outage, there's always so many opportunities to iterate and improve. SREs are a generally curious bunch, and they take any failure as a challenge to try and make the thing that went wrong better in the future. So after each incident, we generally see a few different parallel things spurred that when they all add up together, they make the life a lot better, and you get a highly resilient system at the end of it. So in our case, what did the SREs do to make our region connectivity issues better? The first thing that we implemented was a token-based system for reconnecting, where the first time you connect to Slack, there's definitely that heavy connection process. You need to have that information. But if you get disconnected, why do you need to then do that again? Surely all of that information is in your caches, and it's mostly correct. So in this case, what you can do on Reconnect is hand in a time-based token, and that can then be given downstream. And you can essentially tell them where you got disconnected, and instead of doing the full connection process, you get a TLDR of all the things that happened while you were gone. And then you can just replay that in the client and not have to go through this heavy connection process. It was definitely an improvement. And as you can see, generally throughout a day, this happens quite a lot. You know, you could turn off the Wi-Fi for a minute and come back, and you'll get a successful fast reconnect rather than the old slow process. That's all fine and well, but this buffer that we have downstream, it's limited time. So in our case, it's about 5 minutes. So what happens if it takes you longer than 5 minutes to reconnect after your connection's torn down? You're going to be out of luck, and you're going to have to go through that heavy process. So how can we make things a lot quicker to reconnect and get back in touch with us after there's been a problem? So here's where cloud engineering worked with the SREs of all the edge region services, and came up with automated rules to put in place to try and, as quickly as possible, yank a region from being live. Anytime there was anything that you could predict that would go wrong. So if you had a bunch of Flannel servers that all went offline for some reason, maybe they were pushed a bad update, great, let's detect that, let's automatically yank the region. That way the client can stop banging its head trying to get back into a bad region and instead reconnect somewhere else. And that is what would generally happen when this happens. You know, we get a nice little message to our operations channel saying this region's been disconnected for this reason, and in this case, the engineers helpfully identified who it is that accidentally or purposefully, maybe, who knows, tested this process. So what about other failure scenarios? You could have your ISP not happy talking to a particular edge region, or an engineer might have had a bad day and pulled down a load balancer in a production region. Sometimes you just can't have automated rules for these scenarios, especially for ISP traffic. Like, it's kind of out of your control. So what happens also if you maybe have a haunted load balancer, where when it reaches a certain number of connections, it starts misbehaving and just stops working altogether? That's definitely not a scenario we've ever had happen to us, but if it did happen, maybe then you would need to put in a simple yet before then unnecessary solution of detecting these failures in the client. So if you're trying to connect to a particular region and it's not working, then you can immediately fail back to a different region. it might not be a local region, it might be on the other side of the world, but it's probably operational, which is more than you can say for the one you were trying to connect to. As you can see here, in the past, AP Southeast 2 might have had an issue, and the clients all connected to alternate regions and stopped just repeatedly banging their head against AP Southeast 2 trying to get back in. Having control of the client and the server made us be able to put in place solutions like this. It might not always be possible, but in our case, it helped. So during another incident when the world was mostly on fire and clients couldn't establish new WebSocket connections, an SRE noticed that the Slack API was actually working fine throughout the whole incident and there was no problems whatsoever. If you remember, WebSockets are terminated at the edge, but the API is not. So if you have trouble establishing a WebSocket, how about you go back to old school and you do HTTP API calls directly to the API instead? It's not the real-time Slack that you might be, know and love, but it gives you an option for connectivity in this kind of scenario. You can still poll for messages, you can still send messages, you can still do all the operations, just not real-time. And as it turns out, there's a lot of clients out there in the wild that fitted this scenario where they might not have been able to establish a WebSocket connection because of network connectivity or things like that. And now they have a way to actually connect and communicate. So these and other improvements all added up. And as a result, we had an incident earlier in the year where one of the availability zones in London had a problem. And as you can see here from the AWS notices, they acknowledged that. The client result was pretty transparent. So the clients all detected that they could no longer connect to EUS2. They all decided to reconnect to alternate regions. While they were in the process of doing that reconnection attempt to other regions, they were still able to poll and send messages via the HTTP API. And when they did connect to these alternate regions, they were able to present a fast reconnect token and connect in a streamlined process without causing any downstream problems for any other clients. It all just magically worked. So no engineers got paged. All that happened was there was a webhook to our operations channel where people congregate to see things go wrong. But in this case, it went right. Engineering manager pipes up to say that it's all worked as designed, and some graphs were shared, and it all just magically worked. Except it didn't. But sometimes you have to focus on the wins. But this region, it disconnected itself quite happily, but then it stayed dead for many, many hours. We ended up destroying it and recreating it from scratch because automation makes that job really, really easy. But it turns out we've still got some work to do. We've still got a lot of work to do on making things better after the region comes good, detecting that everything's a success and marking things back online. But it's still a much better scenario than it was a year ago. So in summary, keep an eye on your customers and don't just automate for automate's sake. Try and remember the reasons why you were automating in the first place. Small improvements all add up to make a highly resilient system. You don't need to come up with a silver bullet. Sometimes just a few simple things make things better. And always keep an eye out for haunted load balancers. Thank you.